this slide right here, okay? Numerical weather prediction. So I've kind of warned you about this, that a lot of things we do nowadays has to do with computers. And we spent some time in this chapter on Monday talking about the computers need those initial conditions. Remember we said they can get them from ASOSs or weather buoys or ocean buoys or all sorts of different ways. Heck, you can even slap a measuring device on the bottom of a plane, assuming they know you did it. And as that plane goes from coast to coast, they can actually send you good information that you can use as initial conditions. So those initial conditions are put into a model, okay? So these models, you can only, bless you, make these models if you know understand the science of the atmosphere, okay? So there's different models that actually forecasters can rely on. Sometimes you'll be at a weather site, for instance, Weather Spark, I'm going to say, is a good one, and actually that particular website will tell you which model do you want to go to. And meteorologists pick their model, okay, kind of their thing behind the scenes. So again, it's a computer model, and then you put those initial conditions into your computer model. So a lot of times there's a smoothing process that goes on before you take this massive amount of data and give it to your computer. If you've ever heard of the term outlier, okay, sometimes you just look at data and you're like, I don't think so. So just imagine giving that to your computer and your computer doesn't know. So basically kind of remove outliers. Another thing of smoothing, and this textbook doesn't talk about this, but another thing of smoothing is if you're missing some data, so I'll kind of grab how do you get your initial conditions? Well, we talked about a lot of them are pretty, not too bad if you're surface. Although, imagine sparsely populated regions like the deserts and that sort of thing. Are you going to have ASOSs out there? Are you going to have weather balloons out there? Maybe a little sparser. So another thing for smoothing is to kind of, we call this extrapolate, kind of fill in some of the blanks. So those two things for smoothing. Then, after your initial conditions, you kind of look at them before you give them to your computer, smooth them out. Then we have kind of, it's called an iterative process, and I call it kind of piggybacking. And actually, it's kind of a visual sort of thing, okay? If this is now, okay, and this is time going forward, okay, what this is trying to say is you take your model that you want to use, you take the initial conditions that somebody gave you, okay, and basically you forecast the weather for, what did I say, 2 minutes. A 2-minute forecast. You're like, oh my gosh, are you serious? Well, you do it really quickly. And then whatever it says your forecast is going to be for 2 minutes, you use those as initial conditions, and you can use the same model and plug them back in, and you go another 2 minutes in advance. So now you're up to 4 minutes. You're like, I hope you're doing this fast, because otherwise, by the time you get it, yeah. Okay, and you keep doing that kind of piggybacking, coming up with a forecast, plugging them back in for initial conditions, marching forward in time to come up with some of these, forecasts that are 1 to 2 days out. That's a lot of crunching, So in fact, historically, I guess, when this whole idea of saying that scientists understood the physics or the science of the atmosphere, and they had these models that you could plug initial conditions in and spit out an answer. Well, that idea came before the advent of computers. So it went something like this. You would plug your initial conditions in and you would get a weather forecast, but it would take you about a week to plug it through. And by then you're like, well, that day is come and gone.
That could be part of why
so yeah.
was so significant.
Yeah, exactly. Then. So we really needed computers to kind of make this whole thing work.
When did they come out with computers?
I don't know when they came up with computers. They've been making progress with computers for a long time. Haven't you ever seen, like, back in...
Those huge, big,
like,
things.
The computers, but even calculators. So if you look at desk calculators, okay, what you guys take for granted and buy it at the Dollar Tree for $1, that used to take up, like, this much space and cost a lot of money. So they've come a long way. So it's kind of a computer man sort of thing working together. Now, the first thing to be split out by the computers are these prognostic charts. Okay, so the computer spits out a forecast. The charts kind of says it would be in a map or kind of tabulated. Okay, so from there though comes the human touch, the human element, like Dow would say. So this model output statistics are where humans are kind of applying their own knowledge, tweaking it a little bit, okay? Kind of, if they know, like this says, if they know the model has a shortcoming, is biased, kind of look for things that they think are an issue. Because they don't want to be wrong, right? The weathermen don't want to be wrong. I don't think they really care.
No, they're wrong sometimes.
Yeah, they're definitely wrong sometimes.
It's raining outside. Nope.
I know. So problems with this whole numerical approach is, one is coming up with the models. So to come up with the models, you have to say that you understand the atmosphere. It's like you understand Mother Nature. Like, well, good luck. So we understand a lot of basics of physics, but Mother Nature is still unpredictable. The other thing, and we'll talk more about this when we talk about chaos and the butterfly effect, is what if they gave you the wrong data? What if all of your weather balloons went haywire and all of the weather balloon data sucked? Okay, your initial conditions are pretty important, and if they're wrong, your forecast is wrong. Sabotage, okay? And then the last one, we said that it just takes a lot of computer time, okay, which may or may not be available. So this is an example of a prognostic chart. If you've seen the movie, is it Space Odyssey, 2001, with HAL, you know, computers running our lives. But anyway, this is what the computer spit back, okay, based upon a particular model. Notice the computer puts in possible precipitation, regions of precipitation. We see a stationary front, we see a cold front, we see a warm front.
Why does the severe weather convective outlook go past or on the left side of the cold front?
Because it's to me it's almost looking like it's kind of crude. This is just hasn't gone through the MOS process.
Okay.
But the other thing, it almost looks to me like an occluded front, where we kind of have an intersection of, you know, and occluded fronts, you can have it on the front and back side of the occluded front, the purple line. So notice though, these are put out by, remember we spent a little bit of time talking about the organization of NOAA, okay, the National Center for Environmental Prediction, National Centers for Environmental Prediction. Okay, so there's a movie called The Butterfly Effect. I've never seen it. I've just kind of seen clips of it. Yeah, I need to see it one of these times. But it basically says this guy, and you can correct me if I'm wrong, but he goes back in time and tries to fix things, and every time he tries to fix things, it basically has consequences. And so the butterfly effect, though, actually before the movie comes out something like this. If a butterfly in South America flaps its wings, actually it has consequences, perturbation consequences, to the atmosphere up here in North America, for instance, the butterfly effect. Like, really? Yeah. So that's kind of how the movie came, and what's the butterfly effect. Now, is it true? Possibly. But kind of related to that is this idea of chaos. And chaos is in everything. There's this study in science called chaos theory. But chaos in this case just means a certain amount of uncertainty, a certain amount of play in all those initial conditions that are fed to your computers. Now, a little bit ago, I kind of teased that, well, what if your weather balloons, all of them went screwy all at once? Okay, now that's not chaos. But when the weather balloon, for instance, sends you a temperature, there is play in that temperature, and that's just inherent to the measuring device. If you've ever heard of tolerance before, that's kind of what I'm talking about. So for instance, if you're measuring a temperature and it's 32 degrees Fahrenheit, well, there's uncertainty, there's play in all measured quantities. And let's just say you had a tolerance of plus or minus 2 degrees. So that doesn't mean it's wrong if it really is 30 degrees and it says it's 32. It just means that it's within the kind of play of what that thermometer can tell you. So go ahead and take this and kind of multiply it through all of the measured quantities that are sent in as initial conditions, and you maybe have room for a disastrous effect. Okay, so that's chaos, and that's kind of the butterfly effect. Okay, now there is something that can combat the butterfly effect and or chaos in your initial conditions that are brought to your forecast by initial conditions, and it's called the ensemble forecasting approach. So if you've ever played in a played or been part of a musical ensemble, okay, so the word ensemble means multiple people working together, and so this is kind of neat. Basically, what you do is for the forecast period, you go ahead and say, I know that my initial conditions have a certain amount of wiggle room in all of my temperatures and all of my pressures and all of my wind speeds and all of my wind directions. So what you do is, with that in mind, go ahead and behind the scenes kind of give an assortment within the tolerance, within the ranges. You feed a kind of different, slightly different initial conditions through to your computer. So for every slightly different initial condition you feed to your computer, it's going to spit out a forecast. It's going to spit out an ensemble of forecasts. Okay? So then what you do, and I have an example to show you, then what you do is, if you look at this ensemble as a whole, now these are all for the same forecast time, okay? These are all the same forecasts, but you look for a pattern, and where you see a pattern where it kind of repeats itself, that gives you confidence that that is the forecast to go with. Okay, and it can also kind of show you if there are any errors in your model. So the example I'm gonna do is one actually that occurred in Europe, Christmas Eve. You know, around here we talk about, and I don't even know what year it was, but the Veterans Day snowstorm. Okay. Anyway, so that's notoriously famous, and so actually here, this Christmas Eve event. So what I'm going to show you is what they forecasted in Europe. Okay, I'm going to show you what it actually did, and then I'm going to show you the ensemble. Okay, so here we go. So each little box is something. So at the very top are 3 boxes. And the first 2 boxes at the top are what they put out. It's the forecast they went with. Okay, and we've talked about isobars in here. If the isobars are close, if the isobars are far apart. The color there is precipitation. Okay, so they have relatively loose isobars, not necessarily any wind, with not a whole lot of precipitation. This third one right here is what it actually did. So the problem with that is basically people were not prepared for the nasty weather they got. Okay, so, and then each one of these is slightly different initial conditions coming up with a different forecast. So hindsight is 20/20, right? So if we go along here and try to kind of look for where we have the potential kind of tight isobars and intense precipitation. Okay, that actually, and if I understand this from the example I'm pulling right, that actually should have kind of, that pattern, that reoccurrence should have kind of thrown up some flags for, maybe we should kind of go with something a little more severe. So, yeah. But again, this is hindsight is 20/20, and this is just an example where ensemble forecasting that they probably didn't have access to, would have been helpful. So that's ensemble forecasting. I think that's pretty cool. And I have a bunch of forwards here. Okay. So remember when we talked about kind of the overall hierarchy of NOAA, the National Oceanic and Atmospheric Administration. Okay. Well, kind of one branch of them are the forecast offices. So these would be your people kind of right before you get the weather forecast. So they wade through the prognostic charts from the computers. They wade through forecasts that were put out based upon prog charts by the National Centers for Environmental Prediction. And then they do one last twist on it. Okay. And they can base their twist upon just how they're feeling that day, hopefully not. They can actually base their kind of final decision on what they know about the region. That includes the topography of the region, the time of year, and then they'll put it forth. Oh yeah, I forgot this. So what is looking at this topic without looking at a few bloopers? So I've chosen just a few bloopers to watch. Actually, they kind of have their issues, but again, you know, you can relate if you've ever had to give a speech or be in front of people.
I did that once.
I've done that before, unfortunately. Yeah, you just start laughing and you just can't stop.
I've never done that.
Left crying.
So these are kind of some other little kind of variations on the numerical weather forecasting. They're not actually all have to do with computers. We'll see what you guys think. So for instance, persistence forecasting, no computer required. No computer required. Persistence forecasting says if something persists or somebody is persistent, that means they just keep at it. So according to persistence forecasting, what you have today is what you'll have tomorrow. No, bless you. No computer required. Not necessarily computer required for the next one either. Climatological forecasting, you're like, dude, climates, of course, is like a 30-year average of the conditions of the atmosphere for a general region, general time of year. So basically, you just say, well, you know, when spring comes, it's going to get warmer. It's going to be wetter. That's it. Okay? So one of the things, though, and actually I kind of tease, but climatological forecasts are kind of what, to me, if you've ever grabbed a farmer's almanac, I buy one every year. There's a section in the farmer's almanac that basically kind of does a long-term outlook, and they do base it on some science. But one of the things that we always wonder is, are we going to have a white Christmas? And so actually this is using climate data, 30-year average, to say who's going to have a white Christmas and who is not. So, yeah. Another one, now to me you would need a computer for this one. It's called the analog method. And basically, if the term analog or analogous situation means that basically it's like Groundhog's Day. You've been here before. Analogous situation. So the same, analogous or related. So what you do basically is look in your archives for a day just like today. So like if 5 years ago the condition of the atmosphere was just like it is now, whatever happened the next day 5 years ago, we can forecast for tomorrow. That's it. Okay, an analogous method, analog method. And then there's trend forecasting, and kind of trend forecasting and nowcasting go together. But this is something that you guys have been doing too. If you look at a map of the United States, the weather conditions, a lot of times we'll kind of look over here to our west to kind of anticipate what we might get. Okay, so we are making use of what we know the trend in weather patterns to be for us here in the Ferrell Cell. If you're in the mid-latitude westerlies, you'd be looking to the west. If you are in the Hadley cell, you're going to be looking to your east, actually. So nowcasting is kind of like that, but it's even a shorter time frame. All right. So a while back, actually, last time we met on Monday, we talked about how do you get those initial conditions from the surface. Well, there are ways of getting initial conditions not from the surface. These would be more indirect methods using satellites. But there are two types of satellites I want to talk to you about. There's this type of satellite, and I don't know if you can tell, but it's actually going from pole to pole. Okay, so it's a polar orbiting satellite. Polar orbiting satellite. So it goes from pole to pole. If you're familiar with the Hubble Space Telescope, the Hubble Space Telescope has the same way that it orbits the Earth. So the physics of it and kind of the momentum of it, in order for it to stay in a stable orbit, these can actually be relatively low. So these guys are relatively low. If you look, though, because they're low, at how much they see during a pass, notice that's relatively small. So it's a relatively small area that they see. The other thing is, I'll show you, when I show you the other type of satellite, you're going to see that the other type of satellite does not do well over the poles, and this one gets really good shots at the poles. So it takes about 100 minutes for it to go around once. Okay, so the other type of satellite looks like this, and it's called a geostationary satellite. Now, the word stationary and geostationary is actually kind of important here. Geostationary. It basically hovers over one part of the Earth. The problem with geostationary satellites, though, is they are limited to only going around the equator. Okay, and again, due to the physics and to make a stable orbit, they are relatively high. So that means they can't see detail, but that means that actually, since they're so high, their swath that they see is bigger. Does that make sense? So less detail, but they can see more, and they kind of hover. Now, in order to hover, basically, as the Earth rotates, they keep up with rotation of the Earth. Okay? So yeah, these are geostationary ones. Okay. So these are better for the mid-latitudes, not good for the poles. Now, both types of satellites can give back 3 different types of images. What they do, and we talked about different energies, electromagnetic radiation, different types of energies. So what they do within the satellites is to change the wavelength that they're looking for. Okay? So they change the wavelength, but what they do is they take a scan and they take that entire scan and they make a single composite image out of it. And it takes about 15 to 30 minutes to make a scan. Okay, so we're going to talk about the 3 different wavelengths to get 3 different types of imagery. Okay. I was trying to think of what it was. It's a series called Z Nation, I think. Yeah. And there's
Never watched it.
there's the guy that has always, or he's kind of in dire straits right now in this season, but he would like send back, he could use satellite imagery to see what was going on with the Z's and stuff. And anyway, I don't think that's probably very accurate. Because haven't you seen on TV shows sometimes they zoom in and they can show you? I don't think that's right. So anyway, the 3 different images, one is visible, and this took me a little while to figure out, but you figure if you guys are the sun, okay, so this is the daytime, this part of the Earth is experiencing daytime. If you have if you're looking at the visible regions of the electromagnetic spectrum, you can't see anything over here, so it only happens in the daytime. The other 2 actually can happen anytime. You don't need visible light. Infrared, remember IR is one wavelength of electromagnetic radiation, and infrared gives you information about heat or thermal imagery. So we had talked a little bit about heat. Basically, if you find your warm spots, that means that there's no clouds. Okay, if you find your nice warm toasty spots. The other thing we talked about with regard to thermal imagery is we said that when we talked about thunderstorms, we said if your cloud tops are really cold, okay, then that means that you have like overshooting tops. Okay, so thermal imagery can definitely give meteorologists information. The last thing is that they change the wavelength. They actually can get at water vapor that's in the air. So you figure the more water vapor, the more likely you are to get some sort of, this says fog or dew or condensation. So we're going to look at some of those images. Okay, so this one is visible. So you figure visible, you're just seeing clouds, and that's actually what you're seeing. So kind of from left to right, or up there in Wisconsin, you can see they actually are having quite the rain event. Over here on the bottom, it says, the caption in your textbook says that it's centered on Iowa, and I really don't think that the bottom right one goes with the upper left one. But those are, you can see the overshooting tops, the little storm cells underneath there. I think that's so cool. So that was visible. This is infrared, and it looks kind of similar to visible, but infrared, we're looking for heat signatures. So what your textbook has done, I think it's quite clever. It went ahead and on that upper left-hand one, identified regions that are free from clouds, so it's all dark, okay, the darker color. And then the other extreme 4, okay, where you see kind of those white blotches, those are actually cooler regions. And then we have water vapor. So this actually is the same day as the first one. Remember we said that here in Wisconsin it was getting hammered. So those are not clouds, those are actually water vapor that's in the air. So it can help in forecasting, and here's kind of all 3 of them put together: visible, infrared, and water vapor. Okay. So in science, a lot of times we'll talk about qualitative things and quantitative things. So qualitative things are things that deal with the quality of the situation. So quantitative things kind of gives it away, maybe. Quantitative means it deals with numbers. So when meteorologists put out a forecast, oftentimes what they say is just qualitative information. Like, is it going to be cloudy, generally cloudy, and if so, how much? Is it partly cloudy? You know, that's qualitative information. Quantitative information would be, what's your high for tomorrow going to be? That's a solid number. So meteorologists put out quantitative forecasts for your high and low temperature for the upcoming days. I think we're all obsessed with looking at those. The other thing, they actually come out with a numerical forecast is probability of precipitation, or POP, probability of precipitation. And if you're like me, it's always a little bit confusing when I kind of try to talk you through it. But when it says a 30% chance of precipitation, you're like, what the heck does that mean? Okay? Well, this is what it means. 30% chance of precipitation. Basically, they have 2 terms to get that 30%. They have a C term, which is confidence that any precipitation will happen in the forecast region. And then they have an A term that is how much of that forecast region will receive precipitation. I think it's confusing. But the example your textbook says is, what if for a forecast region, what if what if the C term, we have confidence, 50% confidence that there'll be some precipitation somewhere in that region. And then what if we think when it happens, 80% of the region is going to be affected? So if you take 0.5 times 0.8, you get 0.4. So they would say that the probability of precipitation is 40%. So I was like, really? You couldn't make it any easier? I guess not. So back to your Farmer's Almanac, okay, long-range forecasts. They actually would be put out by the Climatology Prediction Center, or the CPC, in association with the National Center for Environmental Prediction and the National Weather Service. And so what scientists do to kind of come up with these long-range forecasts for like 3 months kind of chunk at a time is they use climatological data. And though they also use computers. And so they can, it's not straight climatological data. It's like tweaked and massaged. The movie The Day After Tomorrow, I think I already said this before. The movie The Day After Tomorrow, the father figure, actually, he was a climatologist. So things that could affect out like months would be the El Nino La Nina cycle. Okay. Notice your textbook says that when you're transitioning between seasons, it's especially like probably not very accurate. So these are long-range forecasts. The first one's for temperature, the next one's for precipitation. They look kind of like the convective outlook sort of things, which is much more accurate than these. But they just generally say, if they think for these 3 months, is your temperature going to be warmer or cooler? Is your precipitation going to be more or less than usual? And so So this makes sense, based upon all that we've talked about, the person behind the scenes, which would be this young lady sitting kind of in her throne with a bunch of screens in front of her. The person making the decision what to disseminate to the public as a forecast, it would be nice if they kind of had access to a bunch of things at once. So we have these advanced weather interactive processing systems, which, as I understand it, can kind of have an assortment of things. Okay, those including assortment of models, an assortment of data of observational data sources, but you kind of mix and match and kind of come up with something that you're comfortable with. That makes sense to me. Okay, so why are forecasts wrong? Why do they go wrong? Well, one is that, and I've kind of alluded to all of this, I think. One is that when we put the models together to give to our computers, to receive the initial conditions, those models aren't infallible. Okay, we do our best. And the other thing is, believe it or not, computers can't handle the data that we probably like to send them. Another thing, we talked about the butterfly effect and chaos. The effect that even if a measuring device is working properly, there's like a little bit of play in the number that they give it, or that it spits out. And the other one is holes in the data. So I mentioned that if you are here in the desert, there's not going to be somebody, well, let's just put it this way, your measuring stations are probably few and far between. That creates holes. And it'd be nice to know the real deal. So another place we have holes even more than the desert are the oceans. So if this really is a global thing, that what the condition of the atmosphere is going to be for us here, these holes don't help any. Yeah. So the old adage, I wish I could be so bad at my job and keep it, that sort of thing. Be so wrong with regard to my forecasts. So, but with regard to forecast accuracy and error, this actually is pretty intuitive, I think, that your 3-month vague forecasts are going to be less likely to hit the target than your hourly forecasts. The closer reined in it is, the more likely it is to be correct. There's this thing called forecast skill, and what it means is basically how much better did your weatherman predict the weather than you could just predict based upon climatological, what you know about the climate. So forecast skill is hopefully he added something to the weather forecast in what you would have already thought. Okay, so when kind of assessing how well the forecast did or did not do, we kind of have a couple of different options here. The forecast quality, there's no numbers necessarily involved. Forecast accuracy, there actually is a number involved. You can actually pin down, oh, you said the high tomorrow was going to be, or the high today was going to be 90, and it was only 88. So you can actually do a subtraction there and get 2 degrees. Forecast bias. Now, if somebody is biased, that means that their mind is set and they're always kind of leaning one way. Okay, they're biased. If you have, if your forecaster is always, for instance, saying that the high the next day is going to be a certain temperature and it's always under that high, then there should be some scatter. To be unbiased, basically, your forecast should be a little bit under and a little bit over what it really is. So if you do see a trend, bias trend, then you probably need to go track down why that's happening, most likely associated with your model. Okie dokie. So that does it for now. Let's take a look right quick at the homework. There's only 3 questions. Yes, 3 that are due. And they look like this. Let's see what y'all do with it. So the first one has this figure, and it says, which states would experience thunderstorms in the next 6 to 12 hours? So not now, but coming up. who's gonna get hammered with thunderstorms?
Alabama.
Alabama, Tennessee, Kentucky, maybe even Ohio.
Do you want us to explain?
I can't remember, and that one I don't think necessarily explained, but is there an asterisk next to this one?
No.
Okay, so yeah, you need to use complete sentences in your own words. The next one, B, what will the temperatures in Alabama, or will the temperatures in Alabama be rising or falling? In Alabama. Assume that, what do you think, it looks kind of like a squall line?
Yeah.
Yeah,
Like
assume
the
that front.
fall.
Yeah, I bet it's gonna get colder. That one says explain. C, Pennsylvania, will it be warmer or colder?
Colder?
It could be warmer. It almost looks like a warm front's moving to the north.
Well,
I mean, it could, like, use the way
The
that
storm's
wind band
coming
is.
towards Pennsylvania.
yeah, and then it says explain, so I think you could go either way.
Oh, the direction.
To me, doesn't this look like a mid-latitude cyclone? If it is, I'm kind of liking cold front here, I'm liking warm front here, and probably occluded front here. Those are supposed to be my occluded front there. So, I mean, if you said warmer, I'm kind of liking warmer, but I would go either way, you just have to explain it. In which state, New York or Georgia, would cirrus clouds be there? So, Georgia. And why?
Further away.
Yeah. I think what it's talking about is overrunning for this last one. Do you guys remember what that is?
Yeah.
What is overrunning? What's it associated with? Which front is associated with overrunning? Is it warm or cold?
I think it's a warm.
I do too. So if overrunning is associated with a warm front, which one?
New York.
Yeah, New York. What sort of clouds would be here? What sort of clouds are those?
Cumulonimbus.
Yes. CB or cumulonimbus clouds. Yep. So I'm kind of liking the other one, as long as you can explain it. Okay. Next one. We have our next two. So number 3 says, explain the difference between numerical weather prediction and analog method. Okay. So I'm just going to, we just should be fresh in your minds.
So,
No.
analog's like pattern recognition.
Yeah.
The numerical's like computer programs.
Yeah, I think you need a computer, computer models. Yeah. So for the last one, seeing the jet stream the way it is on 2 midwinter days, which of these would southeast United States be warmer? Southeast. So we're talking about here. Which one's going to be warmer? How many people think A? Why do you think A?
The jet stream is further north, whereas in B, the jet stream is a little bit sagged out through the southeast.
Yeah, I'm thinking this is warmer too. Okay. All right then. Awesome. So if you're interested, meet you in the chem lab. Take me minutes to set up or so.